Right, this video is the 100th handwritten high-energy video. So to celebrate this, I will review the older video and the which topics are discussed in the videos, especially in this particle physics and high energy. Such a high-energy physics channel started in the 2022, almost November, I remember. And before that, actually, my journey of the high-energy physics start in the 2019 August. So today is the 100 videos. It's 2025 August. It's almost 6 years ago. Such a particle physics interest started for me with writing the article in the 16 p.m. Physics Mathematics Club in our campus. During the vacation, the summer vacation, I wrote one article about the clock model after reading some particle physics books. And after that, I started studied particle physics myself, even though I didn't learn the quantum mechanics yet because I was a sophomore through the undergrad level. But after that, learning all the courses in the physics department, I started my research in the 2021 March with the neutrino. And I entered the graduate school at the 2023 February, entered the graduate school, and the first papers submit at the 2023 May. So during such academic history, I started such a handwritten high-energy physics video at the 2022 November. Because I want to save my handwriting note. Actually, some times goes, then it's hard to find my writing notes. So such a saving as a video is a very good way to find the old note, and also I can maintain my writing and my studying myself because I should upload the videos weekly. So the first videos start with the neutrino oscillation. Because my research of the particle physics started with the neutrino oscillation at the 2021. So in the first video, I reviewed how the neutrino oscillation can be derived from the quantum mechanics regime, and also the full derivation process for the three flavor cases. And after that, I discussed many simple bugs in the neutrino one. The first one is a master bug, which is a neutrino oscillation in the matter. So as refractive index of the optics, the neutrino has a different effective masses and eigenvalues and eigenstates in the medium. This makes the different oscillation behavior. It is called a master effect. And for the 2021, when I was the graduate in the undergrad level, I started undergrad research with such a topics of the master effect. And based on such research, I started my projects in the graduate level with such neutrinos and other particles like the dark matter, neutrino non-standard interactions based on such a master effect. So I start to learn the neutrino oscillation first at the first stage when I entered the particle physics research area, and I turned to the master effect, and this is the very base for my first research. And also the well-known thing is the neutrino has a small mass. The neutrino oscillation argue that the neutrino has a mass. And to explain such a small neutrino mass, naturally the system mechanism is adopted. So I also explained the mechanism, especially in this video. So I explained the type 1 to the type 3 seesaw mechanisms, and how such a seesaw mechanism can be tested in the experiment. So this is topics of neutrino at the birth stage of my video, and also I should to discuss the other mechanism which can explain the smallness of the neutrino masses, like the radiative neutrino mass, but maybe I will discuss it in the upcoming video. And also not only the neutrino physics in the early stage, also I did equipped about the many basics in the particle physics and the quantum field theory and at the stage. So for example, here is a very basic one in the quantum field theory and the particle physics. For example, the local gauge invariance. In this case, I discussed just abelian case with the U1 gauge symmetry. How the fermion field and the gauge field transform under such a gauge symmetry, and how they couples each other in the covariant derivative form. And I developed this box to the non-abelian gauge symmetry. The important characteristic of the non-abelian theory is there is a self-interactions of the gauge field, and this eventually gives asymptotic freedom behavior for the learning coupling. And for also the non-abelian theory, there is a ghost field, which also contributes to the loop diagram. And also I discussed that how the particle get the mass. Actually, is possible via the coupling with the Higgs. The Higgs potential get the spontaneous symmetry breaking, which means that the vacuum is not invariant under the transformation. So the such a global the gauge symmetry is eventually is broken, and such a non-zero vacuum expectation values of the Higgs gives the other particle mass. For example, the Higgs and the gauge boson coupling gives the gauge boson mass, and the Higgs to the fermion coupling, which is called Yukawa interaction, gives the mass of the fermion. And also I discussed simple derivations in the quantum field theory. For example, the propagator as a two-point correlation function can be induced by the contour integral over the complex plane. And using the results of the propagator, we can deduce the Feynman diagram as a perturbative series with the small coupling, and by the time-dependent perturbation, each term of the coupling's orders can correspond to the Feynman diagram, and from the Feynman law we can calculate as matrix. And also if we consider the higher order Feynman diagram, there is the loop diagram, and we can develop the technique for the loop integral, because there are undetermined loop momentum, and this gives the eventually divergence. And to regularize the divergence, we should add the counter term. The counter term removes the divergence and shifts the coupling eventually, which gives the learning coupling. And as a simple example, we discussed the Piper theory without the higher spin. And in the phenomenological point of view, there are several particles can decay or scatter each other. And one important example is the resonance of the jet boson scattering. For the electron positron scattering to the muon and antimuon, this can be possible by the S-channel jet boson. And near the nanoscale to the jet boson mass, there makes the resonance behavior. And also the one important example of the decay is the muon decay to the electron and the electron neutrino and muon neutrino. This is well-known examples of the wave interaction decay, and I discussed how can we deal with such a three-body decay. And then not only the such a quantum field theory and particle physics, also we discussed some relativistic one as some special relative theory for the unified space-time and general relative theory for the dynamical space-time. These two theories are developed by Einstein in the 20th century. So as a special relative theory, I derived the Lorentz boost based on the space-time diagram. The space and the time becomes a unified quantity, which is called the Ball lattice. And as an example of the general relative theory, we applied especially the cosmology. And in the cosmology is from the dynamical space-time such a characteristics, the universe are actually expanded over the history. So we discussed the epochs of the cosmological expansion by introducing the scale factors and the Hubble parameters. And here, by assuming the uniform and the homogeneous and anisotropic such good conditions, we can assume that the apparel W metric, and by inserting the apparel W metric to the Einstein field equation of the general relativity theory, we can get the Friedmann equation. There is a first and the second Friedmann equation, which is govern the history of the universe, and eventually this gives the lambda CDM model. This is a very basic process of the standard cosmology. And in the first case, also, I talk about the CMB anisotropic very briefly. This is the one different thing. In this discussions, we assume the homogeneous universe, but the CMB anisotropies, like the temperature fluctuations, coming from the inhomogeneities of the universe. So here's we discussed the particle physics and quantum field theories, and the other one is cosmology and relativity theory. That both are very basic in our areas. And my one branch of the research area is neutrinos, but the other branch there is supersymmetry here. Supersymmetry. So at that stage, 2022, for me, I learned the supersymmetry, the CG, at the time. So there is many related videos existed in here. So at the first stage, I started with the superspace formalism with the Grassmann variable, and define the color and the vector shape field. They contain the particle and the subparticle in the one superfield, and inside of the supermultiplet, by using the Grassmann variable, we can define the superfield in terms of the component field, including cylinder superfield. And by using the Grassmann variables again, we can construct the supersymmetric Lagrangians for the color and the vector superfield, and this can be the basic ways to construct the MSS and the minimal supersymmetric standard model. And also there is also the following the many videos of the supersymmetry. Yeah, there are so many, really many ones. So eventually the supersymmetry should be broken. So there are various supersymmetry breaking model. For example, the up-term supersymmetry breaking or D-term supersymmetry breaking. These two are the spontaneously supersymmetry breaking with the non-zero scalar potential. And also there are the other way to break the supersymmetry. This is mediated supersymmetry breaking. So the supersymmetries are broken in the other sector, like the hidden sectors, and it mediate or transfer to the visible sectors. This is called mediation. And there are many mediations models, and the one famous one is GMSB, gaze mediated supersymmetry breaking, and such a GMSB becomes important ones in my research topics. And in the algebraic point of view, the supersymmetry can be constructed by the extensions of the Poincaré's algebra of the space-time symmetry. In the Poincaré algebra, there is a Lorentz boost and rotations and space-time translation, and we can extend this algebra by including the old generators which converse between the fermions and the boson. And also, I discussed how the spinors are represented and transform under such a Poincaré groups or boosts, and constructing the Lorentz invariant Lagrangians of the spinor. Again, some videos discussed and reviewed one more time about the Kara supermultiplet and constructing the Lagrangian, and construct Lagrangian using the such Kara superfields and review both the supersymmetric Lagrangians and MSSM. So here, this is for the neutrino. And this is for the particle physics and QFT, and this is for the cosmology and the relativity theory, and this is for supersymmetry. So this is very early stage when I started such a handwritten physics channel, and also the following videos discuss similar topics but the more advanced one. For example, for the neutrinos branch, I started the neutrinos in the early universe, which is called leptogenesis, as one topic of the research. The leptogenesis is one scenario of the baryogenesis by adopting the heavy matter neutrino. And I discussed briefly about the CP symmetry and the Boltzmann constant, which govern the generated symmetries and the number density of the heavy matter neutrinos in the early universe. And they also discussed the Kasasi parameterizations of the Euclid matrix to satisfy the oscillations data and adopting the active neutrinos mixing. And as advanced topics, I also discussed the mass hierarchy, like the normal hierarchies and the inverted hierarchies of neutrinos, active neutrino generations, and the CP correlation from the surviving probabilities of the neutrinos oscillations one. And as additional and related topics from the leptogenesis, the generated lepton symmetry is transferred to the baryon symmetry via the spiraling process, and such a spiraling process that related to the instanton and some topological solitons. So at the birth stage at the 2023 for me, I don't know the such a detailed box for the topological solitons, so I study myself about the Chern-Simons theory and instanton. This comes from the non-perturbatives epochs and some of the anomaly. And the instanton is called the quantum tunneling epoch, but the spiralons occurs with the finite temperatures epoch with the unstable point. And as beyond standard model, I derived the one decay channels of the heavy neutrino to the gauge boson and the neutrinos, active neutrino, by using the Feynman diagram and some phase-space integrations and setting of the kinematics. So such a calculating of the decay light and the cross action is a very basic and important one in the particle physics. So continuing is the such a particle physics and the quantum field theory approach, I also keeps the basic facts and overviews of the particle physics. For instance, here is the video for the theoretical particle physics when I and the 20th videos of my channels, and also the overviews of the particle physics and the introduction to the such a theoretical and experimental particle physics, such a review for the particle physics series. And here's the very basic box for the particle physics for the QED, the decay light and the cross section by using the barometric golden rule. And how can we deal with the QED starting from the Dirac equation, drawing the Bellman diagram and calculating an matrix. This is a very important one and the basic things in the particle physics. And during that we use a spin summation and the thrust theorem, and such a spin summation on the polarization sums of the spin and the boson gauge boson periods discussed at the time. And as a series in the 2024, twice the live videos like as the what particle physics do, and some resume of the quantum field theory, and the constructing the Lagrangian for the scalar spinors and the vector field as a series of the video. And also for the other area, for the cosmology, I keep the similar thing. Oh yeah, someone's. Yeah. So I drive the scalar field in the expanding universe. Eventually, this gives the equation of the motion like the 2 dots of the pi and the Hubble, pi dot, and the v double derivatives of the pi. This is the equation of the motion of the scalar field in expanding universe, and this term gives Hubble friction, and this term gives oscillation term. This is a simple harmonic oscillator with the friction term. And this equation can be applied to the various ones, like the axion and the wave dark matter and the implantation field or the other scalar field. And I used these formulas in my research as a cornerstone. And also I discussed some dark energy part, like as axion. And the stage of the 2023, I make the presentations in the quantum field theory course about such topics of axion physics. The axion is one solution of the strong speed problem, and from the chiral perturbation theory, we can determine the axion mass from the axion potential, and the axion can be the dark matter candidates by explaining the abundance with the misalignment mechanism. And the other well-known example of dark matter is the WIMP, weakly interactive massive particle. This is the thermal dark matter cases. For the weak interactive couplings and the TV scale of the mass dark matters can explain the dark matter abundance very exactly. Capital omega small h scales near to 0.1. And the WIMP is breathed out, the decouples when the interaction lies and the Hubble expansion light is small and the abundance becomes big. And that there are also the other regime, which is the BIMP, feebly interacting massive particle. If the particle coupling is extremely feeble, then instead of the breathed out, such a particle get the process of the breathing, and also this can explain the dark matter abundance very well. And also the other topics like the recombination of the BBN as a standard well-known early universe one, and the unknown early universe one, like as the implosion theory. In the hard Big Bang theory, there are many problems, like as the horizon problem, blindness one, and to explain such a problem, one can adopt the implosion theory, and how we discussed how the implosions resolve such a problem, and typically the implantation field, the additional scholars, the adoptist for the such implantation theory, and such a scalar field is governed by the such a formula, scalar field in the expanding universe. And in the briefly also, I try to understand the cosmological perturbations from the perturbing matrix and the perturbing substance, but at the last stage, I try some more time for such a dense perturbations in the early universe. And also for the supersymmetry, I keep the along topics. For example, the RG evolutions of the supersymmetric or supersymmetric breaking slopes term. This is the very helpful to and important for me for my research. And the supersymmetry breaking determine the mass spectrums of the particle, and there's several factors like Higgs factor, neutrino one, or fermion one, and such a mass spectrum can be calculated for each model of the supersymmetry breaking. And as one example, I also calculate the C particle decay, the top skulk decay to the neutrino as one example of the decay channel. On the algebraic point of view, the supersymmetry algebra is a G2 extension. So yeah, here's a still many things. So here's a neutrino still, neutrino. Here's a particle physics and the quantum field theory. Here's a still cosmology, and here's a still supersymmetry. Yeah. So yeah, still there are many videos in here. So yeah, some things. Here's some non-neutrino. So here is a neutrino. So this is my first research, the Dirac model and neutrino type oscillations, by adopting the neutrino dark matter, wave dark matter non-standard interactions. Neutrino type can oscillate between Dirac and the Mahalanobis periodically. And this is also the other of my research topic, radiative dimension of the neutrino pair. The neutrino can be emitted in the atomic system with the low energy scale. And this is my second research, second leptogenesis to explain the variant leptogenesis frequencies in the early universe. If the neutrinos has the non-standard interaction with dark matters in the early universe, it can get the dependence of the temperatures, and this makes the leptogenesis occur twice, and the variant leptogenesis generates history with the different devices. And relating to such leptogenesis, I study myself about the topological solution of topological defect. The topological defect is classifications of the mapping from the vacuum state to the spatial infinity. This mapping can be classified homotopy class. And there are several topological defects: kink, or so-called domain wall, vortex, also called the cosmic twin, or monopole and instantion, and the polaron, is the finite temperature effect. And such a topological defect produces in the early universe makes a problem, so-called domain wall problem or cosmic string problem. If the generated domain wall and the cosmic string are too much, then this makes the modifications of the universe history and its evolution, so their abundance should be small. And in the 2025 January, February of my research, such a domain or cosmic string problem should be avoided, so that I study myself about those things. And also I tried the particle physical lectures based on my note. This is not handwritten. This is the PDF part. The particle physical lectures 1 to the 6, but it did not end this very well. There should be more things, but I didn't continue such a lecture. It starts to the natural unit, h bar and c equal to 1, and build with the different spin of build, draw equation, Harley-Strand chirality, and the Brown-Second law. So still particle physics here, and this is topological defect. And also the reviewing the quantum field theory A to the Z. This video is very long, 30 minutes and 40 minutes. I speak very fast at that time because I covered all the things of the quantum field theory, starting from the classical field theory, field quantization, interacting theory, and the higher spin, and the path integral, and the loop, and the renormalization, and the RZ, and the Young-Mills theory and anomaly, all the topics in the quantum field theory, A from A to the Z. And also at the 2024 October, I make the live for the Nobel Physics Prize at that time, and this is the my music video with my friends in the 2025 April, based on my research live. And also for the cosmology, maybe this video is the 2024 summer number density in the early universe, like as the number density and the energy density of the each particle species. This note is made for the high energy physics study in our labs, and also I discussed the impulsion condition and parameters. This is the 2024. So there are the slower parameters epsilon and others. And there is now that there is a series of the cosmological perturbation, but also it did not end very well. There is a instability in the Newtonian regimes, and there are perturbing matrix and perturbing stressors. And after that, I should make the video for the cosmological perturbations. Equation from the Einstein field equations and the solutions, and how such density fluctuations evolved, but I did not make yet. And for the supersymmetry, here the supersymmetry, and here is for the dark matter. So supersymmetry, I made very good videos for the non-renormalizable higher dimensional through Brighton and R priority violation, so-called RPV, and the Suzy breaking slope system, such a weird Lagrangian, but I made very well, but many one does not see that. And relating to this video, I make the gravitational interactions. This is a higher dimensional through brightest, because the gravitational is the spin of the 3 over 2, and there's also gravitational problems I mean their abundance is too large rather than dark matter. This makes a problem. And related to supersymmetry, also I discussed the ground unification theory, GUTs, in here. Maybe this is the 2024. So I study myself about the ground unifications, especially the SU5 group. Does the SU5 representations of the scalar fields, Brownian field, and the gauge boson. And as a phenomenological point of view, the GUT gives the decay of the protons as a part of the violation process. And if we consider the RG learnings, the case coupling for the Z1, Z2 is the universal at the higher scale, almost 10 to the 6, if I remember. And also there are extensions of the SU5 GUT, which are non-minimal, like the SO10 GUT and other one. And also in the supersymmetry, there are the mu problems. The supersymmetry conserving parameters in mu terms should be the similar scale to the stopped mass supersymmetry breaking terms, but this is problem, and there are various mechanisms to resolve the mu problem, like the animal system with the additional singular fields, and the Kim needs mechanisms which can explain the axiom physics simultaneously. And here's some topics discussed together, mixed, like the Colbert's perturbation and the isocolbert's perturbation, and the solution of the mu problem, the supersymmetry, and the preheating from the implications with the parametric resonance. So recently I covered some cosmological perturbation and implications after I attended the cosmology school in the 2025 August. So this month. So the gravitational wave in the early universe, like the topological defect or all the phase transitions, can give such a GW signal. Yes, I participated the panel meeting in 2025 May, and there's a very good slides about the gravitational waves. So I study myself referring that one. And there is a balanced cosmic impulsion model. If the potential of the implanton fields are determined, this can provide sort of the spectral index and scalar tensorities, which can be constraints from the CMBs or other thing. So the such cosmic impulsion model, several ones can be tested. And this is the video series for the cosmology school. From part to part 4, I did not make the part 1. So this is a simple ones for the standard cosmology, and this one's for the implications, reviewing on all the things that are implications, starting from the resolving the problem of the Big Bang theories and the scalar field dynamics, and also for the slower conditions, and how the pre-modular perturbation can be generated from the quantum fluctuation of the implanton field. And the part 4 of the cosmology school, this is very amazing. I learned the CMB now, and the power spectrum, how the pre-modular perturbation gives the power spectrums with the transfer functions by considering the evolutionary part. So this is for the cosmology, cosmology. This is for the supersymmetry. And here now, this is one very advanced topic in the quantum field theory. By considering the loop effect, we can obtain the effective action and effective potential. The effective action play as a role of the generating function of the 1PI diagram, which includes all the quantum loop effect. And yeah, here's the generating function. Maybe I make this 2025 March. And from the effective actions, we can induce the Kalman potential with the loop effect, and by adding the thermal finite complexity effects, the effective thermal potential can be obtained. Also, there are several topics of the beam baryogenesis actions discussed in this video. Yes, also this is about communication and cosmology, how the non-equilibrium dynamics for the particle species that behaves and evolves in the early universe. And related to the such a thermal effect, I discussed the other baryogenesis model rather than the leptogenesis. The one is the upright-ion baryogenesis, which use the deep actions of the supersymmetry, and the other one is the electroweak baryogenesis. Because the such electroweak baryogenesis EWBG requires the burst through the paradigm transition FOPT, and the standard model cannot give such FOPT. By considering the polar temperatures, so this requires additional scalars to extrapolate model. So such electroweak baryogenesis topics are related with the thermal potential. And recently, this is a 98 video. I discussed leptogenesis with the more advanced one, like considering the Wickstrom was out, CPS symmetry, epsilon, and the privacy box and the low scale, like as AR, so the leptogenesis. I discussed it yesterday. And today, yes, 1990s video, there is SM to the PSM. This is a 2024 August TA seminar, still in the particle physics course. And this one is the physics 100th video. So there's so many branches, starting with neutrino, particle physics and quantum field theory, and the cosmology, and the supersymmetry.